So this week we start talking about change, okay? Everything changes in nature, right? And this week, the next week, I think, yes, we will keep exploring different systems that are changing, usually with time, okay? And everything that changes can be expressed by differential equations, right? So today we will explore a special family of differential equations, which is partial differential equations. Partial differential equations. These are equations that usually you have some variable that depends usually on both position and time, okay? Something like this, okay? And usually you have, always you have partial derivatives. Derivative with respect to one variable and with respect to another variable. Something like, let me give you an example. Del squared u over del t squared equals to c squared del squared u over del x squared, for example, okay? What is this equation called? You know, it's a wave equation, right? What if I have del, not del squared, but del u over del t equals d squared, or d, just d. And this one, what is it? Diffusion equation, right? So today we will look at these two equations, okay? So I want to start with heat equation or diffusion equation. They are the same in principle, okay? Heat equation. You might remember something like this: Q equals mc delta T. Do you remember this? Yes, some of you are laughing. So we will write this one for a unit volume element, okay? Are you still laughing? Well, what we do is basically we say that the change, this represents the change, okay? And I basically discretize space into these tiny volumes. So I will write, instead of, I will divide everything with volume. So if I divide this one with volume, what do I get? Q divided by volume is the density times this one, right? So now I will go to the heat equation. I will just write it down and explain the terms. So Cp and C are the same things here. Equals to, let's put it like this, dot K del. This is the most general version of it. So basically, the change in the heat content with respect to time, okay, is equal to how much heat you generation, or you can call it gain, okay? And this term is how much heat you dissipate from that cell. And it depends on the gradient of the temperature, and we will get some feeling about it in a moment, okay? And this is dissipation or diffusion, or simply loss. Okay, so change equals to gain plus loss. Okay? Any questions so far? No questions? So basically look at this equation and let's write it down in one dimension. Let's assume that you are not generating any heat. Okay, so Q dot V equals 0. What do I mean by generation? It means, for example, a nuclear reactor, a core of a nuclear reactor is generating heat, right? You are not heating it from outside, it's actually burning in the inside. We are heat generators, right? So, as I was saying, our body is generating heat, right? Every time a cell does something, ADP goes to ATP, or vice versa? Both of them. Well, whatever you do, you generate heat, right? So this is a case where we don't have heat generation. We just have some temperature profile at the beginning, and it is, so if you compare these parts, so I will just assume that heat conductivity, thermal conductivity, is not depending on space. Basically, you get something like this in 1D. I think this is called thermal diffusivity. Do you see that it's exactly the same as the diffusion equation? So understanding heat equation means understanding diffusion equation, right? So let's think about how we can code this, how we can write a program, computer program that can code this. So what we can do is we can discretize x. So I discretize x, and let's say this is the profile at x depends on x and at certain time t, and I want to find the profile at a later stage. Okay, I want to find tx t plus delta t. Makes sense? Yes. So what I need is I concentrate on one of the cells. Let's say this is xn. This is xn plus 1. This is xn minus 1. Okay. I concentrate on this one, let's say, and the change that will occur on that one will depend on the curvature that I have around it. What do I mean by curvature? So let's say this is txn, this is txn plus 1, no, sorry, n minus 1 xn, and this is txn plus 1. Okay, so how do I define this second derivative? I can think of it as del over del x, del t over del x, right? Then I can write down the difference I have, the slope that I have here minus the slope that I have here divided by delta x. Does it make sense? So basically, let's keep one of the del over del x here, okay? One of the slopes can be written as t xn plus 1 minus t xn divided by delta x, right? This is this slope. Do you see? Then I can write down minus, because I want to take the difference between this slope and this slope, right? Minus txn minus txn minus 1 divided by delta x. Divided by delta x, right? Do you have any questions so far? I'm sorry, I've actually done both of them, right? I just need to divide by delta x here. Do you agree? Anyways, this expression can be, this in the discrete coordinates can be expressed as t xn minus 1 plus t xn plus 1 minus 2 t xn divided by delta x squared. Do you agree? Yes? Any questions so far? No. So I want to equal that to this one, right? I will have some coefficient in front. Let that coefficient be d. So del t over del t equals to d times del squared t over del x squared. So if I take the first order Euler method, okay, then I can just say that txn at a later time stage is txn before plus this expression, right, which is d times t, let me just write it, t plus t minus t xn 2t xn divided by delta x squared. Do you understand my point? Times delta t, of course. Any questions so far? Yes, sorry. So basically what I'm doing is I'm writing this one like this. Sorry, you are right. I think this is... Okay, delete. And I should also delete this one. So basically, this is equal to this one. Does it make better sense? So this is the derivative with respect to time. This is the second derivative with respect to space. Okay? So let's code this and see what comes out. Okay, clear as usual. Let's say I will have 100 grids. Okay, and initially, let's say all grids have 0 temperature. Okay, let's make it 101. Now, I will do the following. I will start with a temperature profile that is something like this. Okay, over here it's t equals 0, over here let's say t equals 1. Don't worry about the coefficients, the how big it is, etc. These kinds of stuff, like is it physical or not, that's a different story. Okay, so I will just say that from 40 to 60, I will set it to 1. Okay? If we plot this, what we have so far, it looks something like, okay, change version 1. It looks like something like this. Do you see it? 0, then you have this one, and then it goes away. Okay? I decided I will go with 100. Okay? I start with something like this. What do you expect to happen next? Just imagine something being really hot in the middle. It will decay, right? What you expect is something like this, etc. Right? Let's see if we get that or not. Of course, we need to write the code for, let's say, t equals 1 to really big number. So let's say I have d equals 1, dx equals 1, dt equals 0.1. Okay, let's say. So I will find the new t going from 2 to n minus 1. So I will skip the edges. The points over here and over here I will skip, because I have these differences that depend on both sides. So I will only run this for these points over here. And this will correspond to keeping this edges at 0 temperature. Okay? I'm just trying to write the simplest code. Okay? The old temperature plus dt times now 2 to n minus 1. What are the points that are always to the right? 3 to n, right? You understand my point? 3 to n. Then what are the points to the left? Now this one you should tell me. 1 to n minus what? 1 to n minus 2, right? Minus 2 times whatever I have here, 2 to n, divided by what? 2 to n minus 1, very good point. Divided by dx squared, right? Now, let's keep plotting this, and I will keep the y limit of the plot between 0 and 1, okay? And I will press draw now. Let's say the time constant is small, so let's see. Is it really dissipating?
Yes.
Everyone sees this? Maybe we should draw with bigger lines. Line width, let's say 3. Okay. So this is really slow because I wanted you to see the effect. I couldn't put it down there anyways. So let's see it really quick, 10 times faster. It is basically doing whatever you expect it to do. Right? Any questions so far? Yes?
How do we get this
This one, 3 to n, those ones. Okay. Okay, how did we get them? So I want to write down so let's say if I go from here to here, this is 2, this is n minus 1. Do you agree with this? Yes. I want to do the following. I want to take this row, okay, and put it, let's call this row txn, okay. So I have my formula minus 2txn. Do you agree with this? What about txn minus 1? I want to have everything that is to the left of every element. Okay, so I go from 1 to n minus 2. Does it make sense? So that corresponds to my txn minus 1 term. And I have also txn plus 1, which are everything to the right of this row. Sorry. This is my original row. And everything to the right can be found by going from 3 to n. Okay? Okay, very good. Now, I want to do the same thing for 2D, if you will allow me. Is it okay if I do it also for 2D? It's very easy. So, in the case of 2D, I write down the same equation one more time. Del t over del t equals to, basically this is the main equation. This is the Laplacian that in 1D Cartesian coordinates corresponds to del squared t over del x squared. What is the same expression in 2D Cartesian coordinates? Yes, this one plus this one, right? Can you guess 3D? Yes, you can guess 3D. But of course there are the cylindrical versions of it, which is, if my memory is not failing me, something like this. And the spherical one is the same thing with r squared outside and inside. Okay? Anyways, just we are going to solve this for 2D, right? Do you know how to do this operation in 2D? Yes? Very good. Tell me. Let's say I have the simplest version like this, right? This is, yeah, go ahead.
You get all the neighbors.
Yes.
You basically write down the same equation, but you add a plus and write one for the y.
Exactly. So let's say this is txn yn. Then this one is txn plus 1 yn. This one is what? You tell me. What is this one? Or you don't tell me. You get the idea, right? So basically del squared t in 2 dimensions basically comes down to t. Okay, I will write it in this form. T plus 0 plus t minus 0 plus t 0 plus t Well, I'm assuming that del x equals to del y, okay? That makes life simpler. 0 minus plus, not plus, minus 4 times t0, 0 divided by del x squared. Okay? Basically, I'm doing del squared t over del x squared plus del squared t over del y squared. Both of them will have minus 2 times t0, right? So if you sum them up, it's 4 times t0. Are you with me? Yes? It's clear? Let's write it down in 2D. Okay. So how do you write things in 2D? I will start by adding another dimension to this matrix. Okay, so it's 1 by n, 1 by n. Let's say 40 by 60, 40 by 60. All of them is 1. You are with me? Then I will simply write down something like this. Then over here, minus 4. And I have these ones. By the way, if you can continue a line by putting 3 dots in MATLAB and taking it to the bottom line, okay?
I think the indices are
yes, the indices here should be exchanged. Was that your point?
Yes.
Okay. So since it's now a 2D plot, now I want to plot it with image scale, I believe.
Well, it wasn't my point. It goes from 3 to n in the x direction, but 2 to n minus 1, for example.
Okay.
Very beginning of the line.
This, by the way, this one is also very beginning. Do you mean very end of the line?
Both of them. I mean, at the beginning, after dt, there is 3 to n in the x direction.
Yes.
But it goes from 2 to n minus 1. Shouldn't it also be 3?
No. This is like, this is keeping the, so this is with respect to x.
Yes.
So I should keep the y row the same. As you can see, over here I keep x the same, x's are the same, and I change y's. Okay? I forgot to write d, but it doesn't matter, d, I took it 1. So axis equal and off. Does it work for you? Do you have any questions? What do you expect to see? Let's see, and then, well, this is like for electronics people to feel at home. This is like a chip, like it was hot, really hot, and then you let it dissipate its heat, and that's what you see, right? Do you feel like home? So let's watch it again with contour plots. Okay. So I will plot contours of it with, okay, let's axis off, and I will plot contours at starting with 0. I will go all the way up to 1. Just okay. something terrible happened. Is this better? Okay, I should also say equal. Sorry. There you go. Are you ready? So you can see you start with these lines and they get more and more curved until they become basically circular, right? So this dissipation, diffusion, all of this, basically they get rid of the edges, right? I actually have one more thing for you in this respect. Maybe this. Don't worry about this one. It's just to produce the pattern. I start with something uh, like that, and you can see that it loses its edges, right? And if you wait for long enough, by the way, this is a different case. In here, I also put some heat generation. Do you see it over here? Basically, you can put some heat generation by simply typing dt times some constant. So every cell is now a heat generator, right? So let's see what happens in the long run. So before you were losing some of the hot contours here, right? Now you will lose them up to some point, but then you will stop losing them because it's also getting hotter and hotter in itself. Do you understand my point? So you can see that you no more lose this one. In fact, this was nice, right? And you get something between. Eventually, you will have some circles in the middle, and it has to go to the boundaries as a square, so you will have square outside, etc. Okay?
Why it has squares?
Because I have boundary condition which tells it that at the boundaries temperature is 0 and the boundary is a square. So it has to find a solution of being quite isotropic in the middle. That's why being a circle, and being anisotropic at the edges, following the boundaries. Okay? You can see that as the heat keeps generating, you even get new contours. I think you will get them in a moment, but let's not wait for them. Okay? Do you have any questions so far? Do you feel like more closer to diffusion, heat dissipation now? Do you? Did you touch it? Okay. Now let's go to. Let's now go to the wave equation. We have like 13 minutes, so. In the case of the wave equation, things are a little bit more complicated because you have second derivative on both sides, right? Let's actually keep this in 1D. I don't want to go to 2D. So this one is done. This one we understand what it means. Basically, you can say the time difference can be represented as some variable del V over del T if I define it as U. Okay? Then, sorry, it's totally wrong. May I go back? Yes. If I define V, something very bad is happening. Okay. Remember all this? Are we at the edge of the paper? That's why this is happening? I don't know. Anyways, so V, let's define it as del U over del T. Then you can define del V over del T as C squared del squared U over del X squared. Okay? So let's try writing the wave equation now. So I will start from scratch again, 100, and I will set everything to 0 at first. And this V over here, I will just type it as du. Okay? In fact, I will take all the time, so it's u of x versus t, all of them at the beginning, I set them to 0. Okay? I'm tempted to cheat. Am I allowed to do that? Can I go through this code instead of writing it? Because it's a little bit more complicated. But I promise I will tell you each line. Okay? Is that okay? Okay. So I will go from 1 to t. What this line is doing is it's telling that until some time, like 0.1 over 2, just oscillate the one end of the spring. So if you have a spring here, something like this portion will be oscillated back and forth just once, and it will stop. So I want to create a wave, right? If I do that, just imagine a spring. If I do that, you will create a wave, right? Something like this that will propagate, hopefully. Is that correct? Of course, I need to solve the equation, the wave equation, for the rest of the places. So this one is a kind of an acceleration, okay? This portion corresponds to this equation, okay? So I basically define this one as ddu. Are you with me? I hope you are. Do you understand everything in here? We just did it for heat equation. Yes? Then from acceleration, I find the velocity by adding to the old velocity acceleration times dt. Does it make sense? Yes? And finally, I find the position by adding to the position velocity times dt. Still makes sense? Yes? So now let's watch what happens. There's a good reason why I called it a bomb. So it was supposed to create this wave, right? But because of the numerical instabilities, it explodes. Okay? So how can I get rid of those numerical instabilities?
Add more points.
Increase the resolution, add more points. Same. What I did was to get rid of that without adding more points. What you can do is you can use one of those numerical tricks. For example, velocity verilette. Can't see. velocity varilet, okay? Which is done in the following sense. So for example, normally what we did here was I found a of t at some time, right? Then I found v of t plus delta t by doing this straightforward Euler integration. I hope it's pronounced Euler, otherwise I'm talking about this guy. Okay? But this is not velocity varilet. This is straightforward first order integration, which explodes in our case. Okay? Velocity varilet does the following. It starts by just writing this down to the next term, up until to the next term, which has 1 over 2 delta t squared at. Do you agree with this? Yes? So now that I know this one, remember that this at is found using x of t. Do you agree with this? The acceleration. At least in our case, it is the case. In our case, it's the case. So using this prediction for xt plus delta t, you can find a t plus delta t. So basically you predict the acceleration. Then you correct the velocity accordingly. Vt, instead of just writing at, you write down something like this, the average of them. Do you understand this point? Now the same code without changing anything. So you can see that here we start by getting the acceleration. I first define acceleration in terms of u. Do you see it? Then the new u is defined as the old one plus dt times v plus dt squared over 2 times acceleration. Do you see it? Then I use the new guess for the next step. I find the acceleration from there, and I do this prediction correction thing. Okay, the same system now works perfectly. Do you see? By the way, is it what you would expect from the wave equation? Since you have, by the way, I'm not solving this part. I keep it at 0, as you can see here, 0, 0. That's why it's being reflected in this way, right? As you would expect. Of course, you could have this point loose. Do you remember what happens when it is loose?
It reflects the same way.
Yeah, yes, it reflects the same way. So I have somewhere here, yes, I called it mirror. So basically what I'm doing here is that I'm taking the last point equal to the previous point. Okay? Let's see what happens this time. It comes, bounces off the same way. Okay? It comes, bounces off the same way. And finally, the wave equation has a special condition in a sense that it can be written, if you go to Wikipedia, it can be written, it can be separated into waves going to the right and to the left, okay? At least in 1D that is the case. So you can write down a very nice absorbing boundary condition. Let me just show it to you. I did it somewhere here, I guess. I basically wrote an absorbing boundary condition, and you can just check it out. So what happens in this case is you start with a wave, it comes to this boundary, and it gets absorbed. Okay? This is a serious business. Let me show you yet another 10,000 citation paper. Perfectly matched layer for the absorption of, this time, electromagnetic waves. Do you know this paper? You keep citing it, right? When you do electromagnetic wave simulations. Okay, I think it's a good place to stop. Take care. All best.